Thank you very much. Yeah, so just to say that I know some people have seen this. Some people have seen this talk before, so this is probably the last time I'm going to give it. And but I did think it was sort of one of the most relevant things for this type of workshop. And of course, I'm very happy to have been invited to Singapore to give this talk and see all the other talks. It's a bit of a trip down memory lane for me because actually I used to live on this street. So this is a picture of me. This is Prince George's Park in the 80s. The point of this picture is not to see how cool my brother and I look, but to see that this building here is the emergency management office, which is right next door. Yeah, and this sign, Prince George's Park, is exactly the same sign as in the 80s, which I thought was quite nice because in Singapore nothing ever stays the same for long. Okay. And also I guess it's a bit sad because it means that I've been associated with the university for my entire life. Just different ones. Okay, so this is joint work with Nick Whiteley, who's also here at the back of the room. The talk is sort of sectioned in a few parts so that people who sort of get exasperated have appropriate times to leave. The first bit is just a review of notation so that the rest of the talk makes sense. The second bit is about variance estimators, which use sort of ancestral information which you can think of as being produced by a particle filter. So in some sense, the main point of the talk is that you can actually very easily and computationally cheaply estimate certain variances associated with the particle approximations that are produced by a particle filter. So that's sort of the main takeaway from the talk. If that's of zero interest to you, then of course, you can also leave now even. That's an appropriate time. Then I'll have some examples where you can see some kind of pictures of the kind of output that you could get from the variance estimators. So you could stick around for that because then the last bit is the theory. So, well, it's only a bit of the theory, right? So if you're not interested, if you're only interested in maybe using the variance estimators, then you don't need to, stay for that bit of the talk, and you can have an early lunch. Okay. So I've also tried to write down some of the notation on the board in case people forget. This slide is just to set notation, right? So the idea of classical Monte Carlo, or one way of thinking about classical Monte Carlo, is that you approximate sums with random variables. So for the whole duration of this talk, everything is on a countable state space, not because we're restricted to countable state spaces, but just because the notation is somehow more elementary. Okay? Everything generalized. So you might have a countable state space X, and you might want to approximate some mu of f, which is just the sum over x of mu x times fx. And if mu is a distribution, then of course mu of 1, I should say that 1 always represents the function that takes any input and outputs 1. Then mu of 1 is equal to 1, and mu of f is actually the expectation of f of x when x is distributed according to mu. Okay? And then of course, in Monte Carlo, we often approximate this kind of sum using this kind of weighted, well, just this average 1 over n times f of zeta I, where the zeta i's are IID from mu. Okay, and we like this at least in situations where it's relevant because it's very simple. And I didn't even put it on the slide, but one of the things that's nice about this kind of approach is that not only do you get an approximation of mu of f through this particle approximation, it's trivial to try and understand what the variance of your approximation is, right? So you can construct, you can do all sorts of nice things to be conservative. You can also come up with asymptotically exact confidence intervals and so on, right? And so the purpose of this talk, or the purpose of the work leading to this talk, is to try and see whether or not we cannot get such simple things also for sequential Monte Carlo. Okay, where obviously the random variables involved are interacting and so on in such a way that it's not immediately obvious how you would get a reasonable variance estimate. Okay, so sequential Monte Carlo, using the notation of Pierre del Moral, is sort of a very nice sort of numerical integration scheme or random numerical integration scheme where you sort of can approximate certain types of sums. Okay, so it always has sort of these ingredients where you have some initial distribution mu, you have a bunch of Markov transition functions, and you have some non-negative potential functions. Okay? So for the purpose of this talk, if you like finite state spaces, you can just think of the m's as transition matrices and the g's as just sort of vectors. Okay? I mean, you don't really lose anything by thinking about things in this kind of sense. Okay, so then once you do that, then you define a bunch of objects, which are the types of objects that you can approximate using sequential Monte Carlo. The first of which you could think of as gamma naught, which is just mu. And then you can recursively define gamma p to be gamma p minus 1 pointwise product with gp minus 1, and then mutated by this transition matrix. So that's like matrix multiplication, vector matrix multiplication, if you like. Okay, and then of course, those gammas, there's no reason that they would actually be distributions because they may not sum to 1. So you can always define a distribution counterpart for the gammas, right? So that's just e to p is gamma p renormalized. Okay, and there's another way you can think about this, which is quite nice. I know this is quite basic for many of the people in this audience, but you can think of e to p as just being this sort of e to p minus 1 reweighted by gp minus 1 through this pointwise product, renormalized, and then mutated by some mp. And you can even think of this as some kind of mapping from distributions to distributions. Okay. So here's an example, and this is obviously one of the main motivating examples. Originally for this type of algorithm, you might have a hidden Markov model where actually these objects are quite natural. Okay? In this case, you might have mu being the initial distribution of your hidden Markov model, so x naught is distributed marginally according to mu. And then you have these transition functions which describe the evolution of this sort of hidden state. And then you have some other Markov transitions, m superscript y, which describe some conditional distribution of your observations given the hidden state. Okay, so that's exactly what this says. Okay, and in this case, the potential functions really just correspond to specific values of mpy, xyp, where usually yp is just some given sort of data record that you've already received. Okay, it's actually quite difficult to look and point. Okay, so then in this case also those gammas and etas have nice interpretations, right? So you can think of gamma naught is of course just eta naught, which is equal to mu, which is just the marginal probability that x naught is equal to x. But you can see that gamma p of x is sort of the probability that xp is equal to x, and the observations y0p minus 1 are the ones that you've been given. And similarly, e to p is sort of the predictive distribution of xp given the observations up to time p minus 1, or the first p observations. Okay? And you can also see things like we can define Zn to be the normalizing constant of gamma n, which is exactly just the marginal probability of the observations, of the first n observations. Okay. Please stop me and ask a question if I'm being unclear. Okay, so one algorithm, which is basically the algorithm that the particle filters or sequential Monte Carlo algorithms kind of closely approximate in a somewhat elegant but perhaps also naive way, is the forward algorithm is an algorithm where you can compute all of these quantities exactly, right, on a finite state space. You just initialize by setting eta naught to be this mu, which is a vector in the finite state space. And then for p is 1 to n, you just sort of do this reweighting, which is just a vector-vector pointwise product, renormalization, and then multiplication by this matrix, right? And you can also, for example, see that you can compute this normalizing constant Zn by just taking a product of sums. Okay? But of course, if x is really large, then you can't really conceivably implement this algorithm, or of course, if x is countably infinite, then you're in trouble. So sequential Monte Carlo, which has a long and storied history, this version sort of appeared already in 1993, but I understand variants of it also were worked on before that by different people. Okay? So in this algorithm, you just basically straightforwardly try and approximate exactly this kind of recursion. Okay? So you have this is the recursion. E to p is equal to phi p of e to p minus 1. And all you do with your sequential Monte Carlo scheme is you always replace e to p with its particle approximation. Okay, so e to pn is always going to be the sum, or it's always going to be the empirical measure associated with a bunch of particles at time p, where zeta naught I are IID from your initial distribution, and actually zeta pi are always IID from the transformation or the mapping phi p applied to this particle approximation. Okay, so in some sense, what's really nice about the algorithm is it's super simple. And also, of course, that it works very well in some scenarios. Okay, and you can also get a nice particle approximation of this Zn by basically following, well, I think I've got it on the next slide. It's like you take a product of the particle approximations of the e to p GPs. Okay, and something that's very nice about this scheme, in addition to its simplicity, is that it has some interesting lack of bias properties and consistency properties. So for example, this one is quite nice. The fact that the expectation of gamma n, capital N of phi, is exactly equal to gamma n of phi. Okay? But unfortunately, it's not true for the eta ends. Okay. So if you want to look at how the algorithm is usually implemented, at least at the highest level, or to see exactly why it's tractable, this is the sort of exact equation, and this is what you do. You sample zeta pi IID from this phi p of e to p minus 1, capital N, which is basically like simulating from a mixture. Okay? This is just renormalization. This is sort of giving you the GP minus 1 zeta p minus 1j's are kind of like the mixture weights, and the MPs sort of give you the distributions associated with your mixture. Okay. So in some sense, you can see it's tractable because this is a finite mixture, right, with capital N components. Okay, and here I just say, well, your normalizing constant estimate is just this product of averages. Okay, so I don't want to dwell too much. This is still the very introductory bit where we just try and understand, well, what kinds of things do I want to understand how to estimate the variance of? But of course, it's nice to know already that, of course, the people have worked on many sort of fundamental results telling you that you might be able to use these kinds of approximations in practice in a wide variety of scenarios. So of course, under weak conditions, Pierre has shown that you get almost sure convergence of both gamma n capital N and eta n capital N as capital N goes to infinity. And similarly, you can look at sort of, well, that's nice and all, but what about how variable they are? Well, under some pretty weak conditions, you can see that actually there's an asymptotic variance, which is basically the limit of n times the variance of gamma n capital N divided by its normalizing constant, the true normalizing constant. And you can see that that's actually equal to a sum of a bunch of terms that depend on the model, obviously. That's why you have these VPNs and the function phi that you're interested in. Okay? And if you're interested instead of the sort of unnormalized guys, so the gammas we usually think of as being unnormalized, where the etas are the normalized guys, the limiting mean squared error of the etas is given by the same functional sigma squared n, but applied to the recentered function phi minus eta n of phi. Okay, does it make sense? So we're going to be wanting to understand, can we approximate this? Can we even approximate sort of just this variance? And can we approximate, of course, this type of asymptotic variance as well? Oh, and we will even show that you can approximate these VPNs, right? Which is sort of the most advanced version. Okay, so before I continue, I just want to say that, of course, I talked about hidden Markov models, but you can approximate very general expectations using this type of methodology. And I think this is also where this type of variance estimation methodology might come in even more handy, because people are starting to use sequential Monte Carlo not as the final algorithm always, but sometimes as a subroutine within a more complicated algorithm. And being able to automatically sort of see how variable your estimates are in that context may be even more valuable than just as sort of trying to report an approximate standard error or something. Okay, so here I don't want to dwell on the details, but basically what you do is you can kind of artificially create a sequence of distributions such that your initial distribution is something that you choose, and your final distribution is something that you're interested in, right? Some pi. Okay, and then you can basically construct a certain type of Markov kernel, usually using Monte Carlo Markov chain type ideas. And then you use a particular type of potential function, which depends on your intermediate distributions. And then you get sort of these same types of results applied because, of course, it falls within the general framework of the sequential Monte Carlo type methods. Okay. Okay, so obviously, to put into context, despite heavy use for many years, until recently, the only way people would ever estimate the variance associated with these approximations would be basically to run the algorithm a bunch of times and see how variable it is. And of course, that's very nice. That has very nice properties. But it can be very impractical in situations where this is really taking up most of the computational time of your whole algorithm, right? So you can't really just say, if your particle filter takes 3 days to run, you're not going to run it 100 times, basically. Okay? Or if you're using it as a subroutine within a larger algorithm and it eats up almost all the time, you don't want to run it 100 times instead of once, right? You just want to run it once. Okay? So we provide, in this work that I'm talking about, we provide an estimate of the variance basically as a byproduct of running a single particle filter, which extends Chan and Lai's breakthrough contribution. I don't know if Chan is here. I've never met him, but he's based at NUS. That's too bad. Maybe I will never meet him. That's okay. And so that was a breakthrough in 2013, which was very interesting, and I think many people didn't realize that there was a variance estimator in that paper. So one of the things I like to do is also try and popularize the fact that they also have a very nice variance estimator that you might use in your own work. Okay? But we also extend their variance estimator in some ways because their variance estimator kind of only treats this, trying to approximate this type of quantity, whereas we approximate also this type of quantity and these types of quantities and so on. Okay, so now to the real meat, hopefully, although this is mainly still sort of descriptive, right? So the theory bit comes right at the end, if you remember. Okay, so the main step when you actually run this algorithm is to sample from this mixture. And if you've been following closely, you might realize that, I keep talking about ancestral stuff somewhere, or at least in the abstract or at the beginning of the talk, but actually there's no ancestral information at all in this algorithm so far, right? However, when people actually implement this type of sampling IID from this mixture, they actually, it's at that point that they start to think about ancestral information, okay? So when you simulate from a mixture like this, one of the most basic ways to do it is to do it in a two-stage process. And this also happens to be computationally efficient. So first you sample IID some sort of mixture indicators, if you'd like, AP minus 1I from a categorical distribution that is given by these mixture weights, right? And then once you've got your mixture indicator, you sample zeta pi independently from the corresponding mixture component, if you'd like. Okay? And it's at this point that we can think of ancestors, because we can think of these mixture indicators as sort of being the index of the ancestor of zeta pi because of the way that we then simulate this guy from zeta p minus 1, AP minus 1I. Okay, so there's a sort of genealogical structure in the algorithm. Okay, which of course, for people who are familiar with sequential Monte Carlo, they know already that this genealogical structure is very much how many people think about these types of algorithms. Okay, but it's important. So this is the index of the ancestor, and it's by that route that we think about ancestral information. And here's a kind of diagram showing some pictures. So basically, this is a very small particle system with little n being 3, capital N being 4. The arrows basically represent, if there's an arrow from one particle to another particle, it means this particle is the ancestor of that particle, basically. Hopefully that's pretty straightforward. I've colored them because you can see that actually this guy has this guy as an ancestor, this guy as an ancestor, this guy as an ancestor, and the red guy has this guy as an ancestor, and they have these two have a sort of shared ancestor at time 1. Okay. And if you think about an ancestral lineage, it's sort of just tracing back, for example, all the way back in time, and you can think of just the indices of the ancestors as being the lineage. Okay, and also you can think of the Eve index of a particle, say the Eve index of this particle is 4, right? And the Eve index of this particle is also 4. The Eve index of this particle is 2, right? So you can have Eve indices at any time, and it involves tracing the lineage back and looking at the index of the time 0 ancestor. And it turns out for the variance estimators, at least for the simplest one, the Eve index, or keeping track of the Eve indices, is the only thing you need to do, right? Which is also why it makes it very computationally inexpensive. Okay, so the first variance estimator, which is hopefully quite simple, it's basically, you can think of this capital V, little n, capital N of phi as being the predictive, the approximation of the predictive expectation of eta n of phi, minus some stuff that depends on capital N and little n, and then you have some sum that basically involves the phi, some phi that you're interested in, where you do some summing over indices of particles that don't share the same Eve index. Okay? You can re-express this in different ways, so you can see that it's an order n computation, not an order n squared computation, like everything else in SMC. Okay, so then the result is actually the expectation of gamma n capital N 1 squared, or Zn if you like. The normalizing constant estimate multiplied by this variance estimator is exactly the variance of gamma n of phi, right? And you can also look at other things, like as capital N goes to infinity, this will converge to the asymptotic variance of phi, and as And similarly, if you do recentering using the empirical estimate of e to n of phi, then you also get a consistent estimate of the asymptotic variance, or the asymptotic MSE of this e to n of phi. Okay? So the computational cost for this variance estimator is really free. Like when I've implemented it, it takes no time compared to actually running the particle filter, because what you do is you just keep track of the Eve indices recursively through time, right? Which costs very little compared to, for example, evaluating your potential functions or mutating your particles. Okay, you can re-express it so it has more obviously order n computation time. And actually for this particular estimate, so this one, this is exactly some sort of constant multiple of the estimator of Chan and Lai, which you can see that also as capital N goes to infinity, it's a negligible sort of constant factor. Okay? Okay, but of course you can do more. So the interesting thing here is that of course theirs is this one, but sometimes we're very interested in actually the case where this is 1, where we're interested in basically what is an approximation of the variance of the normalizing constant estimate, right? Because that is what is quite often used in sort of particle MCMC schemes and so on. Okay. You can also estimate these terms in the asymptotic variance expansion, right? You can approximate them using some other sort of a little bit more complicated expressions. Actually, they're so complicated, I'm not going to show you the actual expressions, but I will explain at least to some extent where they come from. Okay? But you also get unbiased estimates of the expressions in the asymptotic variance expansion, of the terms in that expansion. Okay? And they're also consistent and so on, as capital N goes to infinity. Okay, this one, however, is not free. In particular, the time complexity is really not much, right? I mean, you have to do some computations. It will usually be much less than the computational cost of running the SMC algorithm. The main issue here is space complexity, because actually, at least the only way we know of to compute these VPNs is to store, you don't have to store all of the particles at every time, but you have to store their potentials at every time. So that's a little n by capital N matrix of real numbers, or floats, or whatever. Okay? So that could be a hindrance in some scenarios where you have a very large value of little n. Okay, so here's some examples. In the following, I haven't talked about any eta hats or gamma hats, so you can basically just ignore them, right? I mean, but just for the sake of precision, some of the things that I show you are basically approximations of eta hat n, which is sort of the updated version of eta n, and gamma hat n is the updated version of gamma n, and whatever. So just don't worry about that. It's basically very similar. Okay, but in the HMM context, for those of you who are familiar, the e to n is like the predictive distribution, and the e to hat n is like the filtering distribution. Okay, and here's an example where we look at what happens to this type of quantity, n times this Vn capital N of phi, as you increase the value of capital N. Okay, so this is log 2n in the denominator. And you can see that the red line here, because this is a tractable model, you know exactly what the asymptotic variance is. You can compute it explicitly. And you can see that if you have 1,000 particles, you're a little bit low, but you have the right value. So these estimators are not unbiased. When you look at just the V by itself, it's not unbiased. It's only by multiplying by the normalizing constant estimate that it becomes squared, that it becomes unbiased. But here you can see that as capital N increases to about 2 to the 16, then actually it's very accurate, and it has some variability. This is one standard deviation. Okay, so that's for the normalizing constant estimate. For the sort of filtering estimate in this case, you also get a similar story. As you increase capital N, you get a better and better estimate of the actual variance. Okay? Okay, and here's an estimate of the VPN terms for the normalizing constant estimate. So for the normalizing constant estimate, this phi is 1. And basically, you can see that there are certain sort of time points in a time series of length 100 that contribute more to the sort of variance of your estimate than others. Okay? And so this is kind of nice. You can see that basically the blue dots are the estimates, or the mean of the estimates. Again, one standard deviation for the length of the bar, and the x's are the true values. So again, these are not unbiased, but they look pretty good, right, for at least a large value of capital N. Okay, and if you want to look at the filtering estimate, well, it's not so interesting basically because most of these are going to be zero due to forgetting properties of the model. But still, you can estimate the actual ones that are important. Okay, or you can see anyway how far back in time you have to go for there to be a significant contribution to the asymptotic variance from a previous time. Okay, so here is maybe something that's more interesting because somehow the variance, those variance terms and so on for hidden Markov models, they're not tractable, so in some sense this does provide the first way to, in a computationally efficient manner, actually approximate those terms to understand your model. In an SMC sampler, which is corresponding to that more general sort of setup you might think of, it's very difficult to get a good handle on how much variance you're going to get in your approximation because it's a function essentially of the intermediate distributions that you've chosen and their corresponding Markov kernels. Right? Those mutation kernels are usually, new p invariant kernels, and actually the expressions for the asymptotic variance, you can work them out. It has to do with sort of how quickly mixing in a non-homogeneous sense these backward products of kernels are. Okay? Okay, but in this case you can still see that you're estimating the variance pretty well. There's no red line here. This is a somewhat simple model. There's no red line because we don't know the truth, but you can imagine that it's going to be pretty close to that blue dot. Okay, so that's for the normalizing constant estimate, and this is for the filtering mean. You can see that in this scenario, actually, the roles are reversed in some sense. Estimating the normalizing constant is much more complicated, is much less complicated than estimating the mean, and that's just because this is a sort of bimodal target distribution where people would actually use an SMC sampler, or it's reflective of a true example. Okay, and similarly, you can look at sort of the asymptotic variance terms. And here you can play with things, right? So some people, when they make an SMC sampler, they know that, oh, well, it involves these new p invariant Markov kernels. And instead of using one, you could maybe cycle them. And many people do cycle them, right? Because they know that basically those Markov kernels improve if you cycle them like 5 or 10 times, right? Or more. So you can look at things like, well, how do the asymptotic variance terms change when you actually change the number of cycles of each kernel that you use, right? So here's a case where you only have one iteration for each kernel, and you have basically, I think, 10 kernels or 11 kernels, yeah? So this is for the normalizing constant, this is for the filtering, or this is for the actual approximation of pi of phi in this case. And then here, where you look at 10 iterations per kernel, and you can see that things have changed dramatically, and not even in a sort of uniform way, right? So here, let's just look at this one. You see that things kind of go up. These are the more significant terms in the asymptotic variance expansion. And here they it becomes a very different story. And they're all reduced in some sense. Okay. These are also reduced, but you can even see that the ones that are most prominent are not even the ones that are most prominent later on. Okay, so some people say, oh, well, I said one of the motivations is that you don't need to do this IID replications of your particle filter to estimate your variance, but some people might say, well, I like doing that, right? I enjoy running multiple particle filters because of the sort of confidence that I have. No, because then, you get really simple variance estimates, right? So you can use all kinds of nice probabilistic inequalities because of the IID nature of the replications. Oops. So this is not a slide about theoretical results. This is more a slide about, well, whenever you have IID replicates, well, due to the lack of bias properties of some of the variance estimators, it's very easy to combine them in a sort of principled way to get consistent estimates of the variance using the replicates. Okay? And so I don't want to go into all the details, but basically this red bar and the red line and the red dot, shows what you get when you sort of combine the variance estimators using the replicates versus just using the basic replicate-based variance estimator. Okay? And at least in this example, again, there's no theory, you can see that basically the red bars are included within the blue bars, right? Indicating that those variance estimators are less variable than just sort of throwing away the structure of the algorithm and just using a simple variance estimator. I hope that makes sense. Okay? Okay, so now we're going on to the theory bit. No one's going for lunch? I mean, in some sense it's difficult, right? Because I can't go into all the theory, right? But I can try and give an example of at least some of the structures in the that we try to exploit in the theory to come up with the estimators and also to understand their consistency. Although actually I'm not going to go through much of the consistency stuff because that was a bit of a nightmare in terms of the proof, and it's quite long. Okay, but sort of, so the first thing that I pointed out was this Chan and Lai breakthrough contribution. What was it for me? The Chan and Lai breakthrough contribution was that they came out with this variance estimator for the predictive distribution or the filtering distribution estimate, right, which we've tried to extend. And the second sort of breakthrough contribution, which sort of allows this type of work, is that there's a good understanding of the non-asymptotic second moment of particle approximations. Okay, and that's due to this paper by Saru, Del Moral, and Guyade, where basically you can look at the second moment of this type of particle approximation, and you can expand it into a sort of sum of very many terms, but which have a very nice sort of expression. Okay, so here you get some dependence. I mean, what's interesting also about this is that here you can see that this bit encodes all of the dependence on capital N that you get from your variance or your second moment, and then you have these are sort of weights, and here you have these sort of mu b of phi times phi. These are sort of measures for a sort of space twice the size, and this is the bit that encodes all of the information about the model, right? So this is the dependence on capital N. This is the dependence on the model, and of course this sum over, I like to think of them as binary strings of length n plus 1, encodes the dependence on the sort of length of the time series. Okay, and these measures are very nice. For those of you who like Del Moral's sort of style of looking at things, then you can think of these mu's as also Feynman-Keck type models, but on an extended state space, and with a particular structure, which is of course derived entirely from the original structure of the simpler model, involving the mu's and the m's and the g's. Okay, so I can think of mu b of phi as being this expectation, a different expectation with respect to some Markov chain, which I will define on the next slide, of phi of xn and xn prime times this product of gp xp and gp xp primes. Okay, and this Markov chain, this bivariate Markov chain, is basically defined by the mu's and the m's, and also this b, right? This b is a binary string. Okay, and of course you can compare this with sort of gamma n of phi, and this is just like a more complicated version of this, right? Which it is. Okay, so we want to look at, well, what is the, so this slide tries to describe what is the law of this bivariate Markov chain, right? And the law of the Markov chain is basically that for a given b, you have a different type of inhomogeneous Markov chain, and the way it evolves is like this. When bp is 0, then xp comes from mp of xp minus 1, and xp prime comes from mp of xp minus 1 prime, right? And if p was 0, it would be mu, right, basically. Okay, so basically when bp is 0, these two xp and xp prime kind of evolve independently according to their corresponding xp minus 1 or xp minus 1 primes. Okay, but when bp is 1, then xp prime is equal to xp, which is drawn from mp of xp minus 1. Okay, that's it. So it's a very simple sort of way of describing a bivariate Markov chain in a way that depends only on b and the m's. Okay, and of course when b is 0, you just have two independent Markov chains, and you could look at this expression, you just have a product of independent things. You can split this in two into the product of two things, and actually mu b of phi times phi in that case is just gamma n of phi squared. Okay. So here's a diagram. Again, when b is 0, or when b is the sort of binary string of all zeros, you just have two independent sort of inhomogeneous Markov chains. When mu is what I call E3, so that's the one where in the third component you have a single 1, all the rest are zeros, then you have this sort of, this chain just evolves independently as always. You can always think of the XP chain as just evolving according to mu and the m's. It's the second chain that's affected by b. So the second chain, this is from mu, m1, m2, but then suddenly when you want to think about this guy, it's just equal to this, right? Instead of having anything to do with this, it's just equal to whatever this guy got, and then it evolves independently afterwards, or conditionally independently afterwards. Okay. Okay, so that's how you think of those mu b's. And then when we want to look at sort of what our particle filter tells us about these mu b's. Okay, so what's interesting somehow is I'm just talking about these mu b's. I'm talking about this funny expression that comes from this non-asymptotic expansion for the second moment. But at the end of the day, what I'm telling you is I can run one particle filter and get an estimate of the variance. So obviously what's going to happen, well, not obviously, but what I'm trying to explain is that what's going to happen is that I'm going to be able to approximate these mu b's using the same particle filter that I use to run my algorithm. I don't need to run a different particle filter. Although Nick and one of his PhD students has actually looked at running a particle filter for exactly this model to get estimates of the variance, which is a sort of different approach. Okay. Okay, so here, I mean, this is a bit text heavy. It's not so easy to explain, but I can try and explain sort of the rough idea. So the way that we're going to try and recover a particle approximation of mu b is by basically tracing ancestries in the particle filter that we've simulated. Okay, and in order to do that, we just define two auxiliary sort of paths. Okay, so in some sense they're simple, it just looks a bit complicated. So the first one is really just an ancestral lineage, right? So we're going to run our particle filter, we're going to pick kn1 uniformly from 1 on n, and then we're going to trace backwards in time and just recover all of the a's in that ancestral lineage. Okay? K2 is only slightly more complicated. Okay? You're again going to sample kn2 uniformly from 1 on n, and you're going to trace back ancestral lineages until, or, you know, and that's fine, but if you happen to collide with the same ancestral lineage that kn1 hit, right, then you're going to allow that one to be the same, but for the previous time, you're going to sample kp minus 1, 2 with a probability proportional to the potentials at that time. Okay, so I've got it in a picture, and here, you know, when you think of this, you can think of this as defining a conditional PMF of these two lineages, and basically that's what this thing is going to encode, and I don't want to talk about it because it's just complicated. Okay, but in principle, it's a simple object. Okay, but it's the conditional PMF of these lineages given all the ancestor indices and given all the particles. Okay, so here's a picture. The red guy is just K1, so you happen to sample 3 uniformly from 1 to 4, and you just trace back. Simple. Okay, and then here's the blue one. That's K. This is KN2. You sample uniformly, you got 4, and you trace back. Oh, you hit this guy, right? So instead of just following the same path backwards, you actually sample this blue, you know, the location of this blue circle according to the potentials at this time. Okay, and then you trace back, and you didn't hit any more red circles, so everything is fine. Okay, and of course this, in some sense, I'm not going to go into all the details, but this is related to E3. So this is related to this mu b sort of diagram, right? It's the one where, you know, this guy, of course, just goes back, and this guy went back 2 times, and on the second time, it hit a red circle, and then it went back 2 more times and didn't hit anymore. Okay, hopefully that makes sense. And then actually, in order to define the particle approximations, that's all you need. You need these k's, and you need, well, their conditional PMF. Okay, so the particle approximation of mu b is, again, some funny term depending on n's and the binary string and so on, multiplied by this normalizing constant estimate squared, and then multiplied by a sum over all k1 and 2 that have that structure, right? That have the same structure as that corresponding b. So this would be the structure of E3. You know, they happen to collide at exactly the right times and not collide at all the other times. Okay? You sum over all of those k1s and 2s such that they correspond to that binary string, and you sum up all of their conditional PMFs. Okay, and I'm not saying that this is computationally efficient. This, in general, for a general B, is going to be a huge sum, and I don't know how to get the value of this sum multiplied by phi and so on in a quick manner for general B, but I can do it for some B's. Okay. And then the theorem says that actually this, so this bit is easy, and this is the bit that motivates the actual estimators. The expectation of mu bn of phi is exactly mu b of phi. Okay? This is the bit that's really, well, at least for us, it was much harder. Okay? But we got there in the end, and you get this sort of consistency result for mu bn of phi. Okay? Okay, and again, you can recall that this is very similar to the form of the capital VNN of phi, and it's because it depends very much on just mu naught n of phi times phi. And in the case where b is 0, all you're thinking about is I want to look at all those ancestral lineages where they don't collide at all, right? That's mu 0. Or that's the interesting sequence of non-collisions corresponding to b being 0. Okay, and you can compute this in O(n) time because it only depends on basically counting up those particles or considering those particles that don't have the same Eve index, right? Okay, and in fact, an unbiased estimator of this is just given by gamma n of phi squared minus this quantity up there, which simplifies to Vn multiplied by the normalizing constant squared. Okay, and if you want to see, I mean, this stuff is really simple. Once you have that kind of structure, you can see, well, the expectation of gamma n of phi is gamma n of phi. The expectation of mu naught n of phi times phi is mu naught of phi times phi, which is just gamma n of phi squared. And actually, that's all you need to see that the variance of gamma n of phi has the right expectation, right? Because you just look, well, you expand, you see this is equal to that, and then you see that, well, this is also equal to that, and then you see, well, this is exactly that guy, right? Okay, so this being the variance estimator, you get that that is equal, its expectation is equal to the variance of interest. Okay. Okay, so I think I'm just repeating some stuff, basically. So this is just to recap. Actually, those variance estimators, Vnn of phi, is basically just has to do with gamma n of phi and the particle approximation of gamma n of phi and the particle approximation of mu naught of phi times phi. Okay, and similarly, actually, the VPN terms correspond to the particle approximations of mu EP of phi times phi and mu naught of phi times phi. Okay, and it just so happens that these ones we can also compute in a computationally efficient manner, but as I alluded to earlier, it requires storing, at least, you know, we only know how to do it by storing the matrix of potential function evaluations at all times. Okay? Again, I'm not going to go into the details. I mean, it's not, the expressions are not simple, at least the way I've written them, but, you know, you can compute them on a computer. That's the important thing. Okay. Oh, and there's something worth noting that in some sense, you know, if you like to see how this is related to the sample variance, at least in the case where little n is 0, well, it's exactly the same, right? N times V naught n of phi, when you're in the case little n being 1, well, your approximation is just a standard Monte Carlo approximation, and the variance estimator is the standard sample variance estimator. Okay? So in some sense, it's an extension of the unbiased sample variance to the case where you have an SMC approximation, which, you know, is still very principled. So it's nice to know that it also has a very simple variance estimator. Okay, and this is almost my last slide, the computational complexity. Just to recap, I mean, one of the things that I'm hoping is that people who do use the standard particle filter with multinomial resampling, for which this theory holds, especially if they're using it in scenarios where they believe it's very accurate, it's free, basically, to implement the variance estimator, right? It really is. So please do it, and then you know, we can have more confidence in understanding what our results are saying. Personally, I'm finding it quite useful to try and understand quickly whether or not I have enough particles, basically. Okay, but I think it will also be useful for tuning algorithms sometimes in order to, you know, see how different tuning parameters affect the VPNs and so on. Okay, but the time complexity for just computing particle filter estimates is order n times little n, right? But the space complexity is order n because you don't store you don't store all the particles when you try and sample the next particle cloud or whatever. Okay, for the Vn, for the simple variance estimator, it's, the time complexity is the same and the space complexity is also the same, and basically it's free, right? For the V's, the time complexity is the same, but the space complexity does require you to store things, which of course could be bad news in some scenarios. Okay. Something that's also nice to know is that, you know, you may have very complicated models. You may be in that kind of situation where, I think Lawrence was talking about implicit models or whatever, where maybe you can sample from the M's, but you cannot evaluate their transition densities, or maybe your M's are Markov kernels, like in SMC samplers. That's not a problem for this type of methodology, because the only thing you need to be able to compute is the GPs and look at the ancestral indices. right? You don't ever need to compute a transition. Okay. So finally, well, there's just some things that, of course, you can know, and many people ask questions around this as well. So as little n goes to infinity, it's well known that the particle system degenerates in some sense. Of course, in that scenario, your variance estimators will also degenerate, right? For the normalizing constant estimate, your variance estimator will become 1, and for the predictive distributions, your variance estimate will become 0. But basically what it means is that if your eaves, if every particle at time little n has the same eave, then it's hard to estimate the variance. But it's also, in some sense, also establishing a connection between the diversity of the eave indices at the final time and the actual variance of your estimator. It's sort of a close connection telling you that usually if you have no diversity of the eave indices at time little n, then your estimators are probably not very good, at least for the normalizing constant. Of course, if you're looking at predictive estimation, or you're looking at the predictive distributions, it's possible to have a terrible particle system but have very good estimates. You know, that's just like that's a little example anyone can do. Okay. Okay, and that also brings us to the next point, where basically, if you're only interested in the e to n's, then of course you might think, well, having all these eave indices at time little n still being diverse is asking too much, right? Because I know that it's not a requirement that there be diversity at that time to have a reasonable variance. And in that case, Jimmy Olsen and Randall Duke have also extended Shannon-Live's work by using some of the theory that we introduced in this paper to come up with sort of fixed lag variance estimators, where instead of going all the way back to time 0, they go back to some fixed lag time before in order to compute biased but still consistent estimators of the variance. Okay? And they call them Enoch indices, and it's of course very practical in these types of scenarios when you have very large little n, but you have good mixing properties of your chain. In the case where you're interested in normalizing constant estimates, that's not going to do you any good, because basically you need to have that diversity to have small variance. Okay. In many situations, this can also just be used as a diagnostic. You know, if Vn capital N of 1 is less than, say, 0.5 or less than, say, 0.01 or whatever, you have some confidence that actually it will be, that the true variance will be small, except, of course, you can come up with pathological examples where it won't be. So maybe some interesting work would go into cleaning up that kind of, trying to clean up statements of that type. You know, like if you have strong mixing conditions or whatever, then you can know for sure that you have a small variance if this is small, using Markov's inequality or whatever. Okay, and that's it. Thank you. How does it depend on? Yeah, so that's an interesting question. I don't know exactly. I think AJ was telling me some people have looked at it already. But I don't know exactly what the results are. I think that for me the more interesting, well, not more interesting, but I think the thing that you might be able to show is more that if the variance is small, the variance estimate will be good, right? And then it's basically, well, how does the actual variance behave as little n increases? That could be a nice route to the answer, right? Does that make sense? Mm-hmm. But in practice, right, if you scale little n capital N linearly with little n, and your variance is, say, 0.1, then I think it's almost impossible for your variance estimator to have a huge variance. It will be close to 0.1, right? But maybe it's something to be formalized, or maybe there is some issue that I just haven't thought of. I think the way we did the proof, I guess maybe you do, but there were so many complications along the way that I'm not confident of having a reasonable variance estimate at the end. Yeah, but maybe it's something to look at. It's not a nice proof, to be honest. I mean, it's nice in that we got the answer, but it's sort of inductive and not very intuitive, right?
So you said you needed the G, but
yeah.
What about if you didn't have that in closed form and you replaced
Well, if the G's that you used in your algorithm were these unbiased estimates of G's, which is completely fine, and were indicators, then you can use them. Basically, you just use whatever G's you actually use in your algorithm, and it will be right. Right? So, because in a way, if you use the real G in the variance estimator, but you use the indicator in, in your actual algorithm, you wouldn't get the right variance estimate because you'd be estimating the variance as if you.
I thought you were saying that you just had to have the measurement density per se.
Yeah, but yeah, no, I mean, actually, this stuff has nothing to do with HMMs per se. It's in Pierre's sort of setup. So the G's don't have to correspond to densities or anything. They're just whatever function you're actually using to weight your particles.
Okay.
Right.
Is it a lot more complicated if you extend to stratified sampling or the multimodal?
I mean, I think the easy answer is I have no idea what you would do, because basically this theory relies very much on the structure of multinomial sampling, and if you try it as well, it's wrong. Like if you estimate the variance using this scheme, but you actually run stratified resampling, the answers don't make sense. I mean, they're not going to be like orders of magnitude off, but the true value could be 0.1, but you'll estimate 0.3, like consistently. Or actually, I think you'll underestimate. I think you'll underestimate because basically stratified resampling will make it look like there's more diversity than you would have got if you were using multinomial.
I was going to ask the same question, but
Yeah.
another related question is whether at the time you compute your variance estimate, could you have computed a Rao-Blackwell type estimator using the ancestry of the same complexity?
So in most cases, actually, there's not much Rao-Blackwellization that I know of that you could use, right? If you're estimating, say, e to n or gamma n, I don't think there's much you can do. If you want to estimate smoothing expectations, of course, one way of thinking of Rao-Blackwellization is to do smoothing, right? And that is very expensive. And I guess maybe you could do some partial Rao-Blackwellization, yeah. You could compute some. I mean, basically, when you run your particle filter forward, you get one ancestry, but that's only one of many possible ancestries, right? So to Rao-Blackwellize, you would sample a few different backward sampling paths. Those are each order capital N, little n, right, to compute each path. And indeed, at least one of those is kind of like computing the VPN variance estimator. But if you just wanted to, yeah, I mean, I guess the answer is, well, it's also that you need to know the MPs to do that, right? To impute ancestries, as far as I know, you usually need to know the transition densities of the MPs. Yeah, but of course you could, and then I wouldn't know how to get the variance estimator, but maybe it would be simple because of the Rao-Blackwellization. The Rao-Blackwellization scheme is sort of a conditionally independent estimator thing, so probably you could do stuff. I don't know how many people actually do partial Rao-Blackwellization in that manner, though.